In this video, we're going to learn the theory behind manometers. Manometers are pressure measurement devices used in fluid mechanics measurements. So before we can look at manometers themselves, we need to look at a little more general topic, and that is how to calculate the pressure difference between any 2 points in a fluid. And this, of course, is 2 points in a fluid that is in a hydrostatic state, because we're still in the static section of the course here. So remember, our pressure field is described by P as a function of x, y, and z. Notice there's no time here because this is all steady state. We're not looking at any time varying problems here. So our pressure field is given by P. So what we want to do is calculate the pressure difference between 2 points in the fluid. So we have 2 points here labeled 1 and 2. We can always join those 2 points with a path. And so we're going to define a path, and we're going to call a tiny little segment of that path, which I've highlighted in red here, dr. So notice this is a very, very short segment denoted by the differential operator in front here, dr. It is a vector because this has some direction. We're moving from 1 to 2 along this particular path, so it is a vector quantity. Now realize, and we should remember this from thermodynamics, the pressure difference between these 2 points is completely independent of what path we take. So the shape of this path doesn't matter. This is just an arbitrary shape to illustrate the point. Now, if we want to calculate the pressure difference between those 2 points, we have to ask ourselves, well, what do we know about the pressure? Well, we know we have the basic hydrostatic equation. So the basic hydrostatic equation will tell us the pressure gradient anywhere in this field. So what we're doing here is learning how to go from the pressure gradient to a pressure difference between 2 points. Well, the way to think of this is if we want to know the pressure difference between these 2 points, we can move along any path. We can move along this path, for example, between those 2 points, and every tiny little step we make, there'll be a change in pressure, which we'll call dP. So that pressure change, dP, as we move a very small distance, dr, is going to be the pressure gradient dotted with dr. So we have a pressure gradient field here. Pressure difference from there to there, dP, is the pressure gradient dot dr. So realize both of these things are vectors, but their dot product is a scalar, or a pressure change. So this is our starting point for calculating a pressure difference from 1 to 2. Remember, this is going to be coming from our basic hydrostatic equation. So this is dP, the very small pressure difference moving from there to there. We still need to add up all those pressure differences, and so we do that by integrating. So our pressure difference, P2 minus P1, is the integral from 1 to 2 of dP. So think of this backwards. You integrate dP from 1 to 2, means add up all the pressure differences as you go along there. You get P2 minus P1. So just substituting in for dP, P2 minus P1 is the integral from 1 to 2 of the pressure gradient dot dr. So this is a fairly important equation to remember. This is the way we calculate the pressure difference between any 2 points in a fluid when we know the pressure gradient. And in this section of the course, information about that pressure gradient is going to come from the basic hydrostatic equation. So this is a very general expression, will work for any hydrostatics problem. Now what we want to do so that we can start to apply this to manometers is look at a little bit more simplified situation. So we're going to look at a truly static fluid. So this fluid is not accelerating in any way, not undergoing linear acceleration or solid body rotation. It's just a fluid sitting in a tank. So you can think of this as an aquarium. So we have our acceleration due to gravity showing on here, our g vector pointing downwards. We have our z coordinate defined here. So notice we are working in an x, y, z coordinate system, a Cartesian coordinate system, but I'm only showing the z coordinate on this sketch, and we'll see why. Turns out only the z coordinate is relevant in this particular problem. So we have our z coordinate pointing up and our g pointing down. And because of that, g, for this particular problem where I've defined z in this way, g is equal to minus gk. So the g here, without any vector sign on the top, is just the magnitude, so that would be 9.81 meters per second squared in SI, and its direction is in the minus k hat direction, because this is pointing down and this is pointing up. So the direction of g is in the minus k hat direction. So that is what g looks like for this particular scenario. Now, another thing I want to point out while we're looking at this picture, we have our container here, and this is the surface of the fluid. So this little symbol here that we're going to see occasionally as we go through this particular section of the course, that little triangle indicates that that's a so-called free surface. And a free surface is a surface of the liquid, in this case, that is exposed to atmosphere. So this is an open tank is what that is saying. So we want to look for that symbol in problems later on when we're doing them, and it means that surface is at atmospheric pressure. That's the significance of it. So with this, we now want to figure out a way to calculate changes in pressure as we move around in this particular fluid. So we're going to take the expression we had in the previous slide, pressure difference between any 2 points in the fluid, and apply it to this situation where g is given by this expression. So our basic hydrostatic equation is the starting point for this, because it is going to tell us what the pressure gradient is anywhere in this fluid. First thing we do is realize that the acceleration in this case is 0. This is just a static fluid, so we can cross off the acceleration. So if we expand our pressure gradient using the vector gradient operator, the left-hand side of this equation, partial p partial x in the I direction, plus partial p partial y in the j direction, plus partial p partial z in the k direction. And that equals rho g. So that's all that's left on this side after the acceleration is canceled. So now we want to take our expression for g in the coordinate system that we're working in for this particular problem and put it in there. And we do that, we can rewrite that as minus rho g k hat. So this is our expression for the pressure gradient in this particular problem. Now if we think about this, take a look at the left-hand side here. We have I, j, and k components. On the right-hand side, we only have a k component. In other words, on the right-hand side, the I and j components are 0. So that tells us right away that this pressure gradient and this pressure gradient is 0. Well, that makes perfect sense, because that means as we move in the x direction or as we move in the y direction in that stagnant fluid, the pressure doesn't change. And we sort of know that from common sense. If we move horizontally in a swimming pool, the pressure doesn't change. It's when we move up and down that the pressure changes. Well, this is how the math has taken care of that, is the right-hand side of this equation only has a k component. So it's only this pressure gradient that is non-zero. The pressure gradient connected to moving up and down in the direction we defined as z. So right away we will be able to ignore the first two terms of the left-hand side here. Now, we also want to take a look at our dr. So in this particular case, we're working with a Cartesian coordinate system, so a x, y, z coordinate system. So our expression for dr is always going to be dxi plus dyj plus dzk. This can be used to describe any path moving from one point to another in a Cartesian coordinate system. Different paths are just going to have different relationships between the dx, the dy, and the dz. That's all. These aren't necessarily all exactly the same size. As we're moving along some arbitrarily shaped path, dx, dy, and dz will all be different sizes to follow along that path. But a general expression for any path in Cartesian coordinate systems is this here. So now the next thing that we need to do is calculate the dot product between these two vectors. So our pressure gradient vector and our dr vector. And if we do that, our pressure gradient vector only has a k component, as we've noticed. So there's not going to be any contribution of the I and j components. So we just take minus rho g multiplied by dz. So the result of that dot product is minus rho g dz. Notice this is a scalar because it's a dot product resulting from two vectors. So now we're ready to calculate the pressure difference between any 2 points in this stagnant fluid. Here's our definition. We take our dot product and put it in there, bringing the minus sign out front. And so this pressure difference is going to be the integral from 1 to 2 of rho g dz. Now here's where we make a couple of common assumptions. We have to be careful about these assumptions and make sure they're valid in any particular example or question that we might be doing. If we assume that rho and g are both constant everywhere inside of this container, then we can take the rho and the g outside of the integral, and all we have is the integral from 1 to 2 of dz. So that can be solved fairly easily. That's just minus rho g z2 minus z1. So if we're willing to say rho and g are constant, and if there is no acceleration in the fluid and it's in a hydrostatic state, then this is how we can calculate changes in pressure as we move from place to place in that fluid. And it turns out the only thing important about our location is the z coordinate, so moving up and down. Moving in and out of the screen or left to right doesn't make any difference to the pressure. It's only moving up and down that does that. So this is our first look at applying our equation to calculate the pressure difference between 2 points in a fluid to a simplified case where there's no acceleration and where the fluid is in a hydrostatic state. Now, this highlights a couple of assumptions we'll need to be listing whenever we go through this process, and that is rho and g are constant. Now, as long as it's a reasonably sized container, then certainly g is going to be constant. You would have to be looking at a very, very large elevation change for the very small change in g to be significant. So that's certainly a very good assumption. But realize we're also assuming that density is constant. So we would have to be careful about doing this in a case where the density is changing or where there's some stratification of some kind where the density isn't constant. So you do need to be careful about both of those assumptions. So now with this in hand, we want to turn our attention to manometers. So first of all, a little bit about manometers and why they're still used in the lab quite a bit. Well, first of all, in terms of their advantages, they're very, very simple to operate and they're very, very low cost. Some of the disadvantages are they have very poor dynamic response, and we'll talk a little bit more about that when we see them. They tend to be quite bulky, take up a lot of space, and also they have very limited range. They cannot measure a very, very wide range of pressures very easily. So we'll keep in mind these things as we take a look at what a manometer is. So there's a lot of different configurations of manometers, and the lab is going to go into this in quite a bit of detail. You'll see several different styles of manometers in the first lab in the course, but the basic idea is this. If we had a chamber here, in this case it's a container of air, and we wanted to know what the pressure of the air was, one way to do that is with a manometer. So this is just a classic U-tube manometer. So we have usually a transparent tube attached to this container, and it takes on a U shape like this. And the thing that allows us to measure the pressure in here is that we put a manometer fluid in this U-tube. So this manometer fluid I've just shown here with blue shading. Now there's a wide range of fluids we might use in here, Could be water, could be a much more dense fluid, could be a lighter fluid. Part of the design of the manometer is deciding what the manometer fluid is going to be. So if the pressure in this air tank is higher than atmospheric pressure, then what will happen is it will push the manometer fluid down on this side, and it will subsequently raise up on this side. So notice this particular manometer tube is open to atmospheric pressure here. So here we have atmospheric pressure. So here we must have some pressure higher than atmospheric because it's pushing this side down. So in my illustration here, the pressure here is higher than atmospheric pressure. If this was at a pressure lower than atmospheric pressure, then the deflection in these two legs of the manometer would just be switched. So some things that are important here is the distance between these two surfaces. So typically that would be read off of a scale that's mounted behind these manometer legs. So there'd be a graduated scale so that we could actually read off this distance h conveniently. And I'm also going to label these 2 points here. This air manometer fluid interface I'm going to label A, and this manometer fluid to atmosphere interface I'm going to label point B. So we put a coordinate system on here and we identified what direction G is, and this is all exactly the same as that pressure distribution in a static fluid discussion that we just had. So that means that we can use the equation that we developed there in this situation. So the pressure difference from B to A, so PB minus PA, is going to be minus the density of the manometer fluid. So notice I have a subscript M on here to indicate that the proper density here is of this manometer fluid, this blue fluid, times G times ZB minus ZA. And of course, ZB minus ZA is just H. So we'll be able to eliminate that and put H in here. Now the other thing we're going to do in the next step here is we're going to set PB equal to 0. So I'm saying the pressure at this point is 0. So what that means is that the PA that I get out of this is going to be a gauge pressure. And a gauge pressure is a pressure measured relative to the local atmospheric pressure. So by setting local atmospheric pressure to 0 here, the PA will be a gauge pressure. If we set PB to atmospheric pressure, perhaps 101 kilopascals or whatever it happens to be, then our PA would be an absolute pressure. But we're going to set PB to 0 to get a gauge pressure. So the other thing that we're saying here is that the pressure in this chamber, P1, I'm calling that, is equal to PA. In other words, the pressure here is equal to the pressure down here at this air manometer fluid interface. Well, what I'm essentially saying there is that as I move up and down in this air, in other words, as I move from this location down to here, the pressure changes are negligible. So I'm neglecting pressure changes that happen in the air because it presumably has a much, much lower density than this manometer fluid. So indicate that here by saying P1 is equal to PA. No pressure changes as we move up and down in the air. So when we do that, we can rewrite this equation then as just P1 is equal to the density of the manometer fluid times G times H. So this is how this instrument would work. We would know the density of our manometer fluid that we chose. G would be 9.81. We would read this distance off of a scale mounted behind the two legs of the manometer, and we can calculate the pressure that it's measuring, so the pressure in this air chamber in this particular example, as just the density of the manometer fluid times G times H. So a very convenient way to measure the pressure in the lab. And it's also used in industry somewhat. Now, if we go back to some of the advantages and disadvantages that I listed, notice this is a very simple device. We just need to read this H, multiply it by some number, and we get the pressure in there right away. There's no electronics involved. nothing like that. No power supply required or anything. So it's a very simple device and easy to use in remote locations or wherever we need to. Some of the disadvantages, though, I said that it has very poor dynamic response. Well, if this air pressure were changing with time rapidly, this is a very, very slow device to respond to that because there's inertia in that manometer fluid. It needs to rise up in one leg and down in another leg. And if there's an unsteady pressure, this is a very bad way to measure that pressure. And also, if this interface is moving up and down rapidly, it's going to be very, very difficult to read or to estimate what that H is. So quite poor dynamic response. Another problem with manometers is you can see what's going to happen here. If this air pressure, for whatever reason, gets too high, the manometer fluid could blow right out of this right leg here. So there's relatively limited range of pressures that these can measure easily. So, like I said, in the first lab in the course, you're going to see basic manometers that look like this, and you're going to see a couple of variations on this as well. Manometers can be designed in different ways for different purposes. They can be made to be extremely sensitive, and one of the manometers that you'll see in the lab is an inclined manometer, where this measurement leg isn't vertical, but instead it's at an angle. So small pressure changes give relatively large deflections of the manometer fluid along the manometer tube. But you'll see all of those variations on the theme in the lab. So that's the end of the first module in the course. It's not the end of the statics section though. The next module is going to continue on in fluid statics, and we'll be looking at forces and moments on submerged surfaces. So we'll see you in module 2.